Okay, so I'm Frederic. Call me Fred. But okay, so I'm gonna tell you. I think of all the tools I learned maybe over the last few years, there are several that are very spectacular. We can think of SVM and all the classification and regression. I think are very useful. But the dimensionality reduction, PCA, and Gaussian Process Factor Analysis is my personal favorite. So this is why, and this is the one that I've been using. Since I know PCA, I've been using it, and now I moved on to like the next level is the Gaussian Process Factor Analysis. So I'm very happy to tell you about this technique. I work hard to make the talk as simple as possible. I think I'm gonna reach everyone here. I'm sure, 100% sure that everybody will understand the concept of PCA by the end of this talk, and you'll get an idea of what Gaussian Process Factor Analysis can do. So I'm going to start exactly like the way, it's not the same image, but exactly the same way that I was introduced to principal component analysis in the machine learning class. So let me ask you this simple question. What is the dimensionality of this data set? I'm going to give you a little hint. So each point is defined by its by a coordinate in x, y, and z. So let me ask you again, what is the dimensionality of these data? Thank you, thank you. So, okay, so yes, it is 3. But what is the true dimensionality of this data? Okay, spoiler alert, get him out of the... Okay, so we start with 3, okay? And let me work you through this little example. So, okay, so yes, the dimensionality of the data is 3. Now, I'm cheating a little bit because I don't allow you to move. These were generated with data, and you know, with the camera, sometimes you can move around and try to see how the data are the best perceived. In fact, when you can't see it, but trust me, all these data are in fact projected on a single plane. So even though they exist in a three-dimensional space, there's a plane that covers all the points. And this points is given by the equation at the top that is, it's z. In fact, the coordinate z of the data is equal to its coordinate x plus its coordinate y. So at this point, one thing we can do is simply drop the third dimension and actually represent these data in 2 dimensions by using this plane as a frame of reference. So now we started with 3-dimensional data, and at this point, we didn't lose any information. So the data that was originally described by 3 coordinates can now be described in the same way using only 2 coordinates. So you see, this is like the basic. We suddenly drop 1 dimension. Remember that the talk is about dimensionality reduction. So this is now I'm going to ask you a question. You just heard about linear classifiers. Do you guys see a pattern in these data? Okay, what is it? It is a straight line. This is nice. That's not the pattern I was expecting. But this pattern, in fact, what it tells us that the x variable and the y variable are in fact correlated. So that as x gets greater, y also has a tendency to be greater. But that's not the pattern I was looking for. There's another pattern in data, in terms of classifiers. Yeah, apparently there's 2 clusters, so 2 classes of data. It's just that those data are noisy. In fact, I'm going to tell you it's a Gaussian noise. So the two clusters have a mean, but they also but data also tend to be like around the mean, but I mean never centered on the mean, but never like actually on the mean, but only around. So there's 2 clusters. Now that we saw linear classifiers, Nathan, I'm going to ask you what is the decision boundary that can classify, that can be applied to these 2 clusters, that would fit with these 2 clusters. Just the shape of the decision boundary. It is a line which is described by, the equation of a linear equation, yeah. Okay, so the answer is to make a decision boundary here, you need to define it as y is equal to m time x plus b. Okay, this is a linear equation. Did you notice that there's 2 variables, x and y? So the decision boundary is in a 2-dimensional space. So these data apparently are only exist in 2 dimensions. Okay, and this is actually an accurate result, and this is a good decision boundary for the problem. We're going to try to work it to simplify the problem a little bit. So let me suggest one approach. What if we define 2 vectors that are aligned along, okay, so the two vectors that I define here, the first one, the longest one, okay, the length is more or less of a function of the variance in the data, okay, and the align, and so the first, the two vectors are orthogonal. It means that it's just a display artifact, but in fact these two vectors are normal to each other. That is, they have a right angle in between. Okay, the first vector is aligned in the direction of the maximum of variance in the data, while the second vector is aligned in the given that the maximum variance has been captured by the first vector, the second vector is aligned towards the second direction in which it captured the most variance. Okay, now I'm suggesting that we could take these two vectors as a reference frame to represent the data. Okay, and now we're going to call the first axis that is aligned along the longest vector as the first component, and the second axis along the second vector as the second component. And we're going to represent this data in this new reference frame. So you see the rotation that just has been applied on the data. So you see, a rotation is simply a linear operation on a set of data. Now I'm going to ask you again, my dear friend Nathan, what is the line that accurately separates these two clusters of data? And that's exactly it. So x's equals to 0. So while before we had a decision boundary that was defined in 2 dimensions, our new decision boundary, after applying the linear operation, is now defined using only one variable, that is x equals to 0. And you see, with x is equal to 0, we have the best decision boundary for this data. Actually, I say the best. I make the assumption that actually that this is the exact number that is the best. Truly, if we were to do some kind of linear algorithm on these data, maybe it would find something that is close to 0, but maybe not exactly on 0. But this is simply due to the variability in the data. Yep. Well, this is part of this happens, shit happens, like they say. The thing is that when you do a linear classifiers, sorry? In fact, I define it's a third problem. I generated the data according to a rule. And the thing that this is what happens, just like Nathan was presenting a classifiers with a 90% degree performance, 90% of performance. And this is in fact the point that you see. There's in fact two points that are definitely two red points that are definitely on the side of the blue. And this is where the 10% of error comes from. Is that the data? I mean, even if we wanted to do like the best classifiers ever, there's no way that the point that lands in the middle of the blue cluster will be classified as red while all the others are blue. No, this is part of the thing, and this is in fact when it comes to I mean the how do you say that? How are the data easily discriminable? No, and sometimes you have two classes that no, like this is in fact the simple ROC problem. No, sometimes when the two clusters of data completely overlap, even the best classifier in the world won't be able to tell them apart. No, you need more information. So, so does that answer your question? No, I'm sorry. No, okay, no. This is not a classifier. This is so the color here represents the true class of the data. So we went from 3 dimensions. We went through a linear decision boundary that was defined in 2 dimensions. Now we have a decision boundary that is defined in 1 dimension, and our data has 2 dimensions. So there's some kind of how to say that, inconsistency here. In fact, since our decision boundary is defined in only 1 dimension, it happens that we're not using the information contained in 2nd dimension. So we're going to drop another dimension. We went from 3 dimensions. Now we're going to represent the data using only 1 dimension, like our friend Matthew suggested. And in fact, this is the same classifier. Okay, and this is the linear classifier that would have worked in 3 dimensions. In 3 dimensions, it would have required to be defined by a plane. In 2nd dimension, it was a line which has two variables. And now, after just doing linear operations on our data, we end up with this representation that the decision boundary is simply a constant, and we use only 1 variable to represent the data in this new space of representation. Does that? Yes. Yes. This is a very good observation. I'm going to get back to it. Yeah, this is a very good observation. I'm going to get back to it in a second. But this is a very, very good observation. I'm going to get back to it. Yes? The idea here is to find the first component tries to capture the maximum of variance as possible. So the axis is aligned towards the direction. I'm sorry? You don't care about for the first one. You don't care about the second one. The second one tries to capture again the maximum of variance, but needs to. But one constraint is that it needs to be orthogonal to the first one. In this case, yes, because it's 2-dimension. If we were in 20-dimension, that wouldn't be as trivial. Okay, I'm just going to work you back the story. So we start with a bunch of data that is in 3-dimension. Luckily, the data was all along a plane, like Navid put the remark. In fact, I'm gonna say it right now. The fact that it all lands on a plane, it means that there's no variance according to this dimension. And in fact, the first dimension that we dropped is exactly like this last one that we dropped. It's just that this one was trivial to drop because there was absolutely no variance that was explained in this dimension. But in fact, when you okay, so I'm just going to work the story and just remember that there was no variance that was perpendicular to the plane that was initially dropped. Okay, so we found the drop. We managed to represent the 2 dimensions. Then we tried to explain most of the variance using 2 dimensions. We applied a linear operation to rotate the data in the 2D plane. We found the best classifier, and we found that the best classifier in this direction was only using 1 dimension, so we dropped the other dimension. Well, this is exactly what the principal component is all about. No, so if you understood that, you understood what the principal component analysis is. Because this is what it does. It does linear transformation. It's just that it does it, usually PCA will be used in much higher dimensionality and tries to reduce. Sometimes, here we're lucky, we can go and reduce dimensional space that we can actually observe. Because you understand that anything that has higher than 3 dimensions cannot be visualized. This is kind of a limit of our perception. But I mean, it's also, I mean, due to the fact that our world is in 3 dimensions. Regardless of the time. So what is the principal component analysis? It's a method that analyzes the data in terms of their variance. It computes an optimal in the sense of the principal component analysis, because other techniques will employ different measure of optimality. But it computes an optimal set of orthogonal axes that represents the data. Also, when I say optimal, it means that the PCA has a unique solution. Okay, it's not something that is stochastic. It's not something. It's something that is deterministic. It's something that if you use the same set of data and you do the PCA twice, you're going to end up with exactly the same solution. The best definition I've ever heard of the PCA, and that makes the most sense, is it finds a linear transformation that transforms a set of correlated variables into a set of uncorrelated variables. Okay, the fact that the components resulting from the PCA are uncorrelated is tied to the fact that they are orthogonal to one another. It also rates those axes in terms of the variance they capture. It makes it possible to drop less or non-important dimensions as to simplify the problem. This is what we did. That is, the classifier was done using the dimension that captured the maximum variability. We were able to drop the second dimension because there was in fact, because there was less variability that was explained in the second dimension. It's not always as simple, but the third dimension that we dropped, that is the first one that we dropped in the beginning because the data were aligned with the plane, was one that was explaining absolutely no variance. There was no decision that could be based on this dimension since there was absolutely no variance in data. If all the data represented according to this first dimension that we dropped, the one of the plane, was giving all the same value. Okay, they were all on the Z axis, on the Z plane. And this process of dropping dimensions is of great use in image compression. So often in image compression, JPEG, although I was discussing with my friend here about the JPEG, I didn't find that JPEG is actually a PCA. I'm not sure if it's actually a linear transformation, but the idea is that you can try to find a frame of representation of data and then drop a little bit of the information in data, but the idea is that you don't drop a significant part of the data. I'm gonna get over that. I'm gonna go over that again later. So how is the PCA done? Okay, this is kind of the math part. Okay, I'm gonna go over quickly. So it computes. So you need to compute the covariance matrix. Okay, I remind you that the covariance is the covariance matrix. I remind you that the correlation is a normalization of the variance, so of the covariance. So sometimes correlation is a word that speaks more, especially to non-mathematicians. Sometimes correlation is a word that speaks more than if I say covariance. So the idea here is that if it works for you, just think in terms of some kind of measure of correlation between the two variables. Just like, I don't remember, someone noticed, it's Greg noticed that the two variables in the beginning, the x and the y, were along some kind of axis. This is an indication of correlation. This is an indication of covariance. Then, once you have this covariance matrix, you compute the eigenvector and eigenvalues of the covariance matrix. Now, I'm sure I lost a lot of people using these eigenwords. The thing with, I started to understand what was the eigenvectors and eigenvalues by studying actually PCA. The way that you need to interpret it, in this case, a valid interpretation in this case is that the eigenvectors and the eigenvalues are in fact describing the direction in which the energy of the covariance matrix is directed. So the eigenvectors tells you the vectors in which there's a certain amount of energy or certain amount of variance, and the eigenvalues tells you how much of this variance is aligned in this direction. Okay, think about that when you're going to go to bed tonight. But I think this is, if you want to start to understand the idea of eigenvalues, eigenvectors, think of understanding PCA. And I tell you, this is where it started to, I started to understand the concept. Yes? It's going to be the fact, if you think in terms of eigenvectors, okay, one properties of the eigenvectors, when it comes to a positive semi-definite matrix, okay, this is a special case in terms of mathematics, you are guaranteed that all the eigenvectors are going to be orthogonal. Okay, but so far you don't know, when you have like these eigenvectors, you don't know, I mean, how much variance you capture. It is when you look at the eigenvalues. The higher the eigenvalues, the more energy is in this direction. And eigenvectors and eigenvalues come in pairs. Yes? Yeah. So where like the derivative will be equal to 0? Okay, the direction, yeah, okay. But I think, I mean, the true interpretation is that along the eigenvectors, those are some direction. I know that if you go on the wiki, it tells you that it is the directions in which you kind of, you don't change the direction of the matrix. Is that right? Or there's some kind of property. When you apply a multiplication with the eigenvector, okay. Okay. Yeah. Yes, there's an analytical solution for matrix. Yeah. In fact, it's using the trace. I don't remember. I'm going to try that. But in fact, once you found this set of vectors and eigenvalues, just because it is the definition of eigenvector and eigenvalues, in fact, it's going to satisfy the equation that you see at the bottom. A is the matrix. A multiplied by one eigenvectors will give you the same result as the eigenvalue times this eigenvector. The thing is that there's not a single eigenvector and there's not a single eigenvalue. In fact, you're going to end up with as much eigenvectors and eigenvalues as you have dimensions in the data. So if we apply it to the original data, the sample problem I presented you earlier, it was a problem in which the data were defined in 3 dimensions. Well, in fact, it's going to give you 3 eigenvectors and 3 eigenvalues. The thing is that the third eigenvalues, the third in importance is going to be equal to 0. Because all the data were in a plane. Okay, the thing is that once you found these eigenvectors, eigenvalues, there's no guarantee that you're going to find them in the right order, but the thing is that you can just sort them after that in order. So like I told you, the eigenvalues and the eigenvector are paired together, so you just sort the eigenvectors, the magnitude of the eigenvalues, and you align the eigenvectors with them, and then this is when you can decide to drop those that have the less importance. So you can select a subset of the eigenvectors to represent your new data. Now, how do you make this decision as which one are the most needed? It's actually something that's going to come in the next slide. But so I told you how to do it. This is like the hard way. The easy way is to do it using Matlab. We all know we're all using Matlab. Matlab has a function that does it. So this is fantastic because we don't have to deal with the details. So in Matlab, there's a function called printComp, principal component, in which you feed in the data in the form of a matrix X. X is an n by p data matrix. N is the number of observations. In our case, often it's going to be trials. And p are the p variables. And in this case, I'm showing a little example after. P will be the number of neurons in our population of neurons. And here, those are discrete data. Usually, it's going to be the mean firing rate, let's say, picked during the memory period of a reach task. So this is the input to the function. So you see it's very simple. This is what we have usually. Trials by rows, and by column is the neurons mean firing rate during the trial. You can have as much neuron as you want here. You can feed in this is the number of neurons is your dimensionality in the input space. And then you feed that into printComp, the function. PrintComp is going to return you three. Actually, the latent is optional output, but I suggest that you take it. So it's going to return you three things: the coef, the score, and the latent. The coef is a p by p matrix. Did you notice that p by p means that you have as much coefficient? I mean, it's a matrix, a square matrix that has same dimension as the number of neurons. The coefficient is in fact the coefficient that makes it possible to transform the data to bring them into the PCA space. You can see the equation next to score. Then it gives you the coef. It gives you the score. The score is an n by p matrix, so it's the same dimension as the input because it is the actual transformation of the input into the PCA space. So this is the score is actually after the transformation. This is the result of the transformation. So it gives you both the reference frame and the data that you fit into represented in this new reference frame. In fact, I give you the equation. The score is in fact equal to x times the coef. Okay, and this is a matrix operation, but this is the actual way to put it. And then and then finally gives you the latent. The latent is the list of eigenvalues. And this I recommend you use it because the latent is using this vector that you can actually determine the number of dimensions that you should keep in your system. This is how you actually decide how many dimensions you're gonna keep. This is a problem. I give you the address at the bottom. This is if you go on this website. This is actually the blog post I published about PCA. It's a problem in which I sort several brands according to their nutritional values. It's actually a third problem I found on the web. It was a problem that was designed for PCA. So you can compute the amount. The equation at the top tells you how to compute the amount of variance, the proportion of the variance that is captured. So it's simply summing the eigenvalues up to the dimensions that are kept and dividing by the sum of all eigenvalues. Okay, and the two graphs at the bottom, the first one on your left gives you the actual magnitude of the eigenvalues for this specific problem. You can see that the first eigenvalue has a value of 7,000. So don't try to interpret the value of the eigenvalues. Okay, just take them as numbers. Don't try to interpret 7,000 what. Okay, there's no solution. There's no answer to this question. It's 7,000. It's a lot. Okay, in fact, it's just in comparison with the others that it makes sense. So the first one was 7,000. The second one was more or less 5,000, and the third one was from here I would call it 300. So you can see that there's some kind of in fact, when you want to choose the number of dimensions that you're going to use, you have to hunt for this kind of elbow in the eigenvalues. So as you at one point, okay, these data, the initial space was 8 dimensions, and here I tell you that In fact, two is satisfying, but I mean, by the book, you should pick only you only need to pick the three first dimensions, because after 3 dimensions, you notice that the fourth, 5, 6, 7, and 8 eigenvalues are absolutely insignificant in regard to the first 3. And then on your left, you can on your right, you can find the actual result from the equation at the top. So you can see that even using the first 2 dimensions, you capture more than 95% of the variance. So this is well satisfying enough for representing your data. Here we the 2 problem I just presented, we reduce down to less than 3 dimensions. It's not something that is de facto. Sometimes you're going to end up, if you start with a state space that sometimes has 150 dimensions, you might end up with a system that has 10 dimensions. I mean, and there's no guarantee also that you're going to have a dimensionality reduction. If you apply this approach on true noise data, blank noise, in fact, you're going to find that you cannot reduce the dimensionality of noise, because, I mean, the data are already non-correlated. So this is about the principal components. Any questions so far? Yes? Yes, it is independent. Yeah, and that is the main property of the principal component, is that each component is independent from the others. And remember the definition of the PCA finds a linear transformation that transforms a set of correlated variables. The correlated variables is the input into a set of uncorrelated variables, and this is the components. Okay, so each component is absolutely uncorrelated with the other. So there's no redundancy in the data. So there's none of the variance that is explained in the first component is going to be captured by any other component, and this is a very important feature of the PCA. Yeah, and this is why the cumulative energy. I say energy here. Don't cite me on that. I mean, you're supposed to use variance. It's just that energy, I think it's just a term that speaks a lot. You see that it's not a normalization. It actually sums up to 1, and it doesn't sums up to like 1.5 if there was actually redundancy across the components. Yes. But the fact that they're orthogonal guarantees you that there's no correlation. Yeah, and it's only possible because the covariance matrix is positive semi-definite. Honestly, I have no idea what it means. We should ask. Leonard left. So, but I mean, it's a special mathematical case. I mean, the people who develop these tools. I mean, I don't know. For us, no, we just understand them. But the people who actually comes with the idea of developing these kind of tools, man, they just yes. It's like I said, it's deterministic. There's an analytical solution. Oh, okay. Okay. In fact, no, this algorithm is not the one that solves the PCA specifically. In fact, the question you're asking is how do you find the set of eigenvectors? I'm sorry. It's not a minimization. It's an analytical solution. It's in fact analog to it was what Grace was saying a little bit, is that you find okay, I already saw how to do it. I don't remember, but you find some kind of if you have only 2 dimensions, I think you find a quadratic expression that is the trace and the form from the trace and the determinant of the matrix, and you end up finding the zeros that correspond to this equation, and the zeros actually ends up being your eigenvectors, if I'm right. Yeah. Here? But you see, if you make it wider, it's going to flip like only at once. Once it's going to be wider than longer, then it's going to flip. No, so this is going to be the first component. This is going to be the second. But in that case, it's always going to be like along these 2 axes, regardless of how wide. It's just that sometimes the first component. I mean, if it gets wider, like I said, this will become the first component. Yeah. The thing is that even if it's at But the thing is that you're gonna have two eigenvalues that are going to be equal, and then you as a human are going to have to make the choice, because the machine is going. The machine doesn't solve the problem for you. It just gives you the analysis. And in fact, in some situation we're gonna see later, here it turned out that the first component was the one that was the best for to make the decision. In some case, however, it's the second component that's going to be the best to make the decision. Just like this problem here, if it gets wider and wider, the most variance is going to be like on this axis, but in fact, no decision can be made on this axis. So then the decoder is going to find that the best dimension to make the decision is actually a second component. So there's also this idea that is, it's not because the first component explains the most variance, that it is the one on which it is the best to make the decision. But I mean, but the PCA just, the idea with the PCA is not actually to, the true idea is just to transform the data. It's not to make a classifier. I'm gonna have to, I'm sorry to turn down the question because I have like still a bunch to go through. I mean, okay, so let me just conclude on PCA. So why using PCA? Okay, if the set of data has a high dimensionality, just like when you're studying, looking at a population of neurons, you often ends up with at least 30 neurons. You know, just if you use an array, 30 tuned neurons, that means that you have probably like 60 or 70 neurons in the total. So when you have a high dimensionality, I ask you that we all make a deal here. When we have a high dimensionality, we always start by using PCA. I tell you, any problem you can think of is always simpler in a lower dimensional space. Always, always. I won't go over the details, but there's a curse with high dimensionality. They call it the curse of dimensionality. The things that it's counterintuitive, but as the dimensionality increase, there are some phenomenon that affects the distribution of data in the space. And the higher you go in dimensionality, the harder it is to work with the data. If you want, we can discuss. I have a very simple example, but I just don't have the time to go over it. Usually not used alone. That is, the PCA just reorganizes the data. It doesn't do anything else. For instance, this is the first step in the Fisher linear discriminant analysis that was introduced by Nathan. So it's the way to start. I don't remember exactly the Fisher, but I remember that you start by doing a PCA. This gives you like some kind of organization of data, and after that you do some other transformation as to turn it into a classifier. The PCA simplifies the problem. Before generating a linear classifier, okay, in the PCA space, this is the Fisher linear discriminant analysis. A PCA before doing clustering is also a valuable approach. So no, just to simplify, like the idea of the PCA is just to simplify the problem, okay? And you have like lots of you can decide to keep one dimension, you keep 10 dimensions. The idea, you can even decide to keep all the dimensions. But the thing is that by doing a PCA, often you're gonna find that you can drop a few dimensions at least. It is a linear transformation. It makes it tractable. You don't actually transform the relationship of the data. No, the fact that it's linear, it's just like, okay, it's hard to visualize, but in fact, you're just changing the point of view and reorganizing the axis relative to each other. But you don't transform the data itself, unlike when it is a nonlinear transformation. To that, I would just make a parallel with a linear filter, for instance. A linear filter, you won't generate new information in other frequencies. No, a linear filter will just deal with with the same frequencies that the input signal is defined in. It's just that it's going to amplify and decrease the importance of one or the others, but it doesn't add information to the signal. A neural network having two layers, but with no nonlinearity, I won't go into the details, more or less perform a PCA. If you reduce the number of of neurons from the first to the second layer, you actually perform more or less of a PCA because it's a linear transformation, and you force the network to represent using less neurons. Okay, so this is just an example. So you see, so this is a PCA applied on some data I got. So this is an actual problem that was involved neurons. So it's a population of 30 neurons. So the input space is in 30 dimensions. I tried to represent 4 different reach directions in this reduced dimension space, and you can see. And what I compare here is the clusters before and after learning. So the shape of the clusters, that is how big they are and how distant they are from one another. So you see, so this is done actually using a Fisher discriminant analysis, and the first step is the PCA to generate this representation space. So what is interesting here is that I have the information coming from 30 neurons, but I present it in 3 dimensions. Okay, but okay, so with GPFA, you're gonna see that we can even go beyond, even deeper into this direction. So dimensionality reduction, fine, it removes dimension. Yeah, we're gonna just. But I'm gonna try to make. Okay, I'm gonna try to make it fast. I'm sorry because the GPFA is very, very interesting, but I have to go a little bit quicker over it. Okay, so dimensionality reduction, fine, it removes dimensions. Now, how about we add 1? Okay, what do you think of a time-based trajectory in a reduced space? And now I see your expression in your face, and this is what I see from here. Hey, what you talking about, Fred? Okay, let me put it this way. Imagine that our data is in the same format as before. There's trials and neurons, but with one extra dimension, time. Okay, so we're not dealing with, so in fact, I said think PSTH, so we're dealing with instant firing rate rather than mean firing rate during a period. We drop all the time relationships between the data point, so we, for just a second, we forget about the time relationship. We take all the data as being independent in regard to time. Then we perform a PCA, then we drop useless dimensions as to do dimensionality reduction like we just saw. And then we finally add back the time relationship. So we trace, so we add the points, there was 1, 2, so we trace the line between the points, just like in a kid's drawings, so how do you call that, dot drawing, how do you call that? And well, this is basically what the Gaussian Process Factor Analysis does. It's just that instead of using the PCA to do the dimensionality reduction, it uses another approach that is called factor analysis. It is slightly different. In fact, it touched the idea of what is the optimal reference frame. But it is more or less of the same idea. I prefer to, PCA is more intuitive to interpret because more people knows about PCA. It means that the time course of, let's say, 30 neurons, apparently I like these numbers, it could be tractable in a reduced dimension space, maybe even as small as 3, so that we can see it. So even if we present the information of 30 neurons, we present it in 3 dimensions, and we can actually track this brain state over time. Here's an example of when we apply this technique to the recording of an NHP, non-human primate, a monkey, presented with gratings of different orientations. T here is 250 milliseconds. This is the time of one trial. Okay, so I present grating to the monkey back to back, and there's 12 orientation. Here I'm only presenting the results from 4. So I don't know if you can see. There's in the middle of the graph. Okay, I'm going to explain. Okay, I'm going to address the issue of the fact that we don't see very well what's going on because we're in 3 dimensions. But take the time to notice that we have the star. I don't know if you saw this, you see the star in the middle. The star represents the initial point at the beginning of the trial where the brain state is. The idea here, and in fact, and if you follow, each point is 20 milliseconds apart from the other. And if you follow the points, you find that in the beginning, all the brain states are more or less in the same region of the space. But after the trial, once the brain state has settled and actually perceived the grating, you see that it moves away from each other. So this is the idea of trajectory. So they start all in a cluster, and then they move each one in their own direction that represents the grating. Here it's in 3 dimensions. Like I said, the time is only represented by the dots. So each dot is 20 milliseconds away. Here I represent the first 3 dimensions plotted against one another. But I would say that even though it is very impressive, I don't know if you like it, but the idea that we can trace the trajectory of the brain state in 3 dimensions, the truth is that there are more than 3 dimensions that are important in this problem. And this is, here I present each component or each factor, and here we talk more in terms of factor, each factor across time. Okay, and I present the 8th first factor. You see that 8 cannot be represented. There's no such thing as visualizing 8 dimensions. So let's take a look at it. Look at the first one. You see that if we were to, in the first one, we see that there's 4 different grating. We can see that the 4 different grating can easily be discriminated from one another. You see that in the beginning, they all start from more or less of the same point. This reflects the fact that in the beginning, the monkey has no idea of what the grating is actually being presented. And over time, we see that in fact, we have to see it as each grating imposes its own trajectory on the brain state. And each one is going to go in their own direction, and they're going to settle more at some distance from one another. So this makes it very simple to trace and understand that this is the state of the brain that we're monitoring here. Then you can see, you can look at the other dimensions. Just a thumb trick, to see when you're presented with this kind of stuff, you can look at the scale to determine what is the equivalent of the magnitude of the eigenvector. So you can see that the first dimension, the scale goes from minus 0.4 to 0.4. So this will be the first component. This is our reference. But look at the last one. It's from 0.03, from minus 0.02 to plus 0.03. You see that there's an order of magnitude of 10 between the first and the last one. Usually when there's an order of magnitude of 10, you can assume that the first one is significant and the last one can be dropped. And so if we work back from the bottom, we can see that, in fact, the dimensionality of the data the useful dimensionality, I'm going to call it like that. In fact, only the first two dimensions, the third one is interesting, fourth one, I mean, but you see that it fades slowly away. And in fact, you see that in the second dimension, you can tell black and red apart, but blue and green are together. So you see, so this is the kind of stuff that often happens. But so the idea is here is that if we were to keep a certain number of dimensions, I will recommend that in fact we keep only one, and this is the first one. The thing is that, like I told you, this analysis was applied to a set of data that contained the trajectories for 12 dimensions. And now I'm just representing 4 dimensions that were taken the most apart. Maybe if we were to try to discriminate between 12 dimensions, we would require to use more. Maybe some dimensions will be better in some case, and other dimensions better in other case. So this is the idea of tracking actual trajectory of the brain state. How is it done? You know what? If there's one thing I'm going to drop today is how it is done. Okay, just it's very interesting, but it's not complicated. I'm going to be honest with you. It's not complicated, but it takes a while to conceptualize. Once you get it, it's very simple, but it takes a while to conceptualize. So I'm going to skip that. How is it done in Matlab? This is like the best part because all the code is available. And I downloaded the code, the toolbox that is published by you and his friends in 2009. This is actually the paper that is a methodology paper that explains this technique. And all the code, I tell you, okay, you feed in spike trains, and it gives you, and the output is more or less of that. I just work a little bit the plotting functions. But otherwise, I tell you, it took me 1 day. Just, in fact, I tell it here, you just need to format your data as to have like a structure that is one by the number of trials. And then in each structure in Matlab, I don't know if people know what it is. I mean, it's very simple. But and then each trial has a trial ID that you need to track, okay, because it gets shuffled in the process. So when you get it at the output, the trial ID is the only indication you have of which trial is which. And then the spike trains of all the neurons. Okay, so it's very, very simple. It's almost straight out of the plexon, I would say. No, and you just feed it and then in it, and it works. And then you have that. Okay, the code comes with samples, with sample data, and with samples of analysis. And actually, I'm going to put a few samples myself after the talk, like within the next month. We're going to do some kind of summary on the web of this seminar, and you're going to have like sample code. So I tell you, don't be afraid about that. It may be a complicated approach. Maybe if you really want to publish it, maybe you need to work a little bit more the understanding. But just to apply it, just the basics, I tell you, it takes 1 day from deciding to do it and to actually get your first results. Okay, what it can be used for? Okay, this is the results that were published by Churchill in 2006. This is applied to actually reach task. Blink, blink, and I was blinking to the sorry to the motor planning people. So what they did here is that you have the cue on set. Target answer, sorry. And then you have like, I don't know if it was a memory task, I think so. But, okay, so you have the target on set that blinks. And then you have the go cue that tells you go start your reach. And then you have the actual movement onset. The thing is, the thing that was explained here is that as you get closer to the actual movement onset, the representation of the information gets tighter. Okay, so it tells you that the monkeys knows more and more certain about what it's going to do as the trial progresses in time and gets closer to the motor onset. I didn't read the paper actually. I cited the paper because I know it's represented there, but I took this picture from you and his friends. Okay, this is a few situations to which this kind of analysis can be applied. Okay, the first one is just switching between brain states. Okay, like discrete state. Okay, this is in fact decoding what the brain thinks. I ask for you to orient your orientation in the regions of the brain that are at the top. Okay, the regions of the brain, just superior colliculus. We have V4, which is where I work. There's MT, in which some of the Dr. Julio Martinez works, and us, we work too, and Dr. Cook also work in this area. We have MPC, which I think is medial parietal cortex, I'm not sure. And we have PMD, in which Dr. Musalam works. So you see that this analysis is actually targeted towards the areas that we are concerned with. Obviously, I mean, it's up to you to see if the task applies. But so the first one in A is simply switch between different states. In B, it's actually decision making. This is the problem. It's Paul Chizek. I don't know if you know the work of Chizek, the race model for decision making. This is exactly this problem. In C, it is some kind. I don't know where this applies. You see, they say LIP. It is when you have some kind of it reaches a state and then a slow decay towards back to normal. Maybe after a saccade or something. I don't know exactly where this applies. And in D, it's actually the convergence towards an attractor. That is, two different situations leads to the same percept. Okay, two different situations leads to the same brain state. So this is a common attractor. So you see that. So I mean, though I see in this tool a link between actually looking at the neurons and making the link with dynamical system analysis. And this is something that is very hard because dynamical system analysis. You know, when we talk of attractors, no sink, source, no this kind of stuff. I mean, in math, it's very well defined for in linear and even nonlinear dynamics. But in terms of the brain, it's very hard because the variables are very noisy. It's not, we don't deal with functions, but we truly deal with recorded information. So for me, it is like, so far the closest link to actually try to establish a relationship between dynamical system analysis. And in fact, in the paper of you, this technique is compared also that, I don't know, but a true dynamical system analysis of the neural state. Okay, here is my example. That is my own results. Okay, it's only a simulation. This is my experiment. This is what I expect to actually prototype the analysis I was going to do. I'm almost done. And here is a few, okay, I just generated a few brain states. I'm not going to go into the details. I hope you're already convinced. And this is the output. You can see that the first, I'm just going to go walk with you through the analysis of the results. Again, it's a simulation. Okay, it's kind of made so that it works. The first dimension, as you can see, and I get back to the problem that is sometimes the first dimension is not the most informative. The first dimension here is dominated by the trial dynamics. And in fact, it just scaled skyrocket to the roof when there's a stimulus that is presented, and goes back to zero when there's no stimulus. Okay, I didn't cover the trials, but so the first one, the first dimension is not very informative. I actually dropped it. The dimension on which and you can look at the order of magnitude of the last three. It goes from 6 to the 6 times 10 minus 6, 8 times 10 times minus 7. So you see the scale of the last three dimensions is completely rules them out completely. In fact, even the fifth dimension can be dropped. It's just that I ended up keeping it for the second phase of the analysis. So you see, so the output, the way to do it is just to, at first you select the dimensions that are informative, and then I ended up with these 4 dimensions, and I also zoom on the time scale of the different dimensions. So my problem is reduced, even though I feed in, I think this problem I feed in 28 neurons or close to 30. And I end up keeping only 4 dimensions. And you can see, for my problem, it was truly the first dimension that was of interest. To truly get it, I should have explained the goal of the experiment. But for me, it was the second dimension that was actually picking up the information I was interested in. That is, just to say, it's just the time that is required to reach a percept as a function of the certainty about this outcome to happen. It just... I mean, the second dimension was picking up the Q. As you can see, there's some pairs. There's some kind of pairs of lines. The 2 lines that are paired together were in fact represented the same Q. The third dimension is, in terms of decoding, I would say, is the most informative. It represents both the Q and the final outcome of the trial. And the last dimension, although it's less significant, also captured the information about the Q. So Gaussian process factor analysis summary, it assumes that the set of neurons, I think this is a very nice way to think of it. It assumes that the set of neurons is an ensemble of noisy sensors, sorry there's an S missing, that informs us on the hidden brain state. So the brain state is something that is only conceptual. It doesn't exist. You don't have a single variable in the brain, that kind of varies and drives all the other neurons. But through this analysis, we can kind of get a handle on it, even though it's something that is just a concept. For those who did machine learning or are interested in the subject, this is a very similar interpretation to a hidden Markov model. It makes it possible to extract factors, each one carrying orthogonal information. Here, in fact, I really mean uncorrelated information about the brain state. So the idea is we're really hunting for this brain state, this conceptual brain state through this tool, but through the neurons that we can actually observe. A large population of neurons can be studied in terms of only a few factors. This is what I did. 30 neurons turns into like, in fact, I only study four dimensions. It is working around the redundancy of the brain. That is, if two neurons behave exactly the same way, well, this is 100% perfect correlation. Then you simply you drop one. This is how the dimensionality is actually reduced. It finds where there's redundancy and drop this redundancy. So it works around the redundancy or the degeneracy of the brain code to extract the true population code. Conclusion, dimensionality reduction as a general data analysis approach is very powerful. It gets rid of redundancy and focus on the most important dimensions of data. Okay, blah, blah, blah. Is there anything? I hope you understood PCA. I mean, this is the first goal. For those who were interested, I hope you also got the sting by the passion of GPFA. I think it's a very, very powerful tool. It was published in 2009. I think this is the kind of analysis you were talking about, population analysis. I think this is the kind of tool that truly, in fact, the fact that it does it in real time, I mean, over time, and dimensionality reduction, I think it makes it like truly a kick-ass tool. And I think the future of computational neuroscience, I mean, at least for people who use arrays, is going to go slowly through this kind of techniques. It's a little bit, like I said, it's not trivial to understand. Once you get it, you feel like it's simple. Honestly, but you can still use it. The code is available. You can still use it and, in fact, take advantage from the fact that other people worked out the problem for you. So this is what I had to say today. I thank you very much. And, yeah.